Okay, good. Yeah, let's get started. So this is some really high-tech stuff. Okay, so thank you everyone for coming to today's SPAR problem set by me, Tom Frew. I studied at the University of Adelaide. I've now graduated and I do lots of problem setting for our competitive programming league, which is called AUCPL. Today I'm going to be taking you through these problems. So let's get started. The first one is called problem G, good night. And basically, we're trying to find where these two lights that blink at various intervals, A and B, will blink at the same time. And more specifically, will they blink at the same time before we fall asleep at some time t? Now, a lot of very fast languages could probably brute force this problem simply by trying every time, do they blink at the same time when t equals 1, t equals 2, t equals 3, blah, blah, blah. Because c is less than or equal to 10 to the 9, but the operations are fairly inexpensive. But the intended solution for this problem uses the lowest common multiple of the numbers. If you remember, we want the lowest time that the two lights blink together, and we want to check if that's before we fall asleep, and that is equal to the lowest common multiple, the lowest number that will divide both of the numbers. The lowest common multiple is equal to A times B divided by the GCD. This is like a very common formula to convert between one and the other. And if you use Euler's algorithm for this, then it will take O of log of n time, which is definitely going to be within which is 10 log of 10 to the 9, very small. Moving on. The next problem is called always prepared, and I might just see if it will stay with me here. Okay, cool. So we have n items for m scouts, and we want to distribute the items amongst the scouts for the minimum weight, and we want at most 2 items per scout. The first observation that you can make is if n is less than or equal to m, then the answer is equal to the weight of the maximum item. That's pretty obvious. You just give each scout 1 item. Some of them you give 0. If there's more, then you have to do something a little bit more complicated. We can sort the weights of the items in ascending order. So here is one that I prepared earlier with 7 items. And let's say we have 4 scouts. This is supposed to be an m. The optimal way to actually distribute these items among the scouts is by taking item number m, which in this case is item 4, which is 6, and item m minus 1, which is item 3, which is 4, and giving that to one scout. And then basically with these 2 pointers, allocating these 2 items to one scout, going 1 left and 1 right, allocating these 2 items to one scout, then going 1 left and 1 right again, allocating these 2 items to one scout, and then eventually your left pointer will be past the start of the array. And then for the rest of the cases, you can give all the other scouts just 1 item. And this will produce the minimum distribution. Why does this produce a minimum distribution? Well, if you pick any 4 numbers, A, B, C, and D, and A is less than B, B is less than C, C is less than D, or less than or equal to, then the optimal—
Tom, can you hear me?
It's always, always, always putting the highest and the lowest elements together. This is A plus D, and the second highest and second lowest elements together, which is B plus C. This will always get you sort of the minimum maximum sum. And this extends. So if we do this in the array, starting with the item that is corresponding to the number of scouts and just allocating pairs outwardly that way, and then for the rest of the big numbers, just giving them to like a single scout, this is guaranteed to be optimal. And the sorting takes O of n log n time. Let's move on. Sorry, I'm at the TikTok office right now, wasting company resources. All right. Might move this a little bit more. Okay. Problem E. Everyone's online. So we want to calculate the number of people who have possibly been online between some pair of times. And we have the sort of order of people who have been last online for one time, and we have the order of people who have been last online for another time. And these are represented as 2 arrays, A and B. Now, instead of computing the number of people who have been online between these 2 times, we can actually invert the problem and try to figure out the people who have not been online between those 2 times. Because the people who have been offline is equal to n minus the people who have been online, and vice versa. Now, I'm going to tell you why this is a bit easier to compute. The first observation we can make for counting people who have been offline is that offline people are a suffix of the second array B. They're a suffix of the second array B because everyone who's been online between A and B are going to be in like ahead of the list in B, compared to the people who have been offline. The people who have been offline are just sort of going to coalesce towards the end. The other observation you can make is that the people who are offline will stay in the same order. If A and B have both not come online, but the last time A was online was before the last time B was online. Well, the last time that A was online, it's still going to be before the last time B was online if neither of them come online between A and B. They're going to retain their same order. And with these types of observations, we can make an algorithm to quickly compute how many people have been offline. We can derive that the maximum number of offline people is equal to the longest suffix of the second array, B, where the positions are listed in increasing order. And those are the initial positions. So what do I mean by that? Well, here's an example. So at first, we have this array A, where the first person, or sorry, the most recent person online has been number 2, then number 5, 1, 3, and 4. What we can do is we can build up an array of these positions. I call this one pos. 2 corresponds to the index 0, 5 corresponds to 1, 1 corresponds to 2, etc. Here is the array B, which is what happens at when I believe it's Maddie comes back online. And in the array B, the most recent person online is number 5, then number 3, and then 2, 1, and 4. Now we can iterate through the back to the front, basically keeping or checking if the current sort of element to the right had a greater initial position than to the element 1 before it. If so, then we know that both of them hadn't come online because they are both at the back of the array or part of that ending suffix, and also their relative order hasn't changed. So let's run through this check. We start at the back of the array with person 4, and their initial position is in fact greater than the position of the person who's 1 to the left. 1's initial position was 2, 4's initial position was 4. So we know that both of them haven't come online. If we do the next one, 1 and 2, again, the initial position of 1 is higher than the initial position of 2. That means that both 2 and 1 haven't come online. They're still in the suffix, and they are still in the same relative order. We can compare 3 and 2 now, but this time it's different. For array A, 2 was online more recently than 3, but now 3 has been online more recently than 2. That means that 2 hasn't come online during this time, but we know that 3 has. So we stop our iteration there. That way, we can sort of count where our index is at, which is at this position. And this number of people are the number of people who've been offline. The longest suffix of people whose relative positions haven't changed. And that answer is 3, or people 4, 1, and 2. This takes n log n time because that's the time it takes to sort a list. And then the rest of the processing is linear. Moving to deceptive directions. Problem D. So this is a problem where you have a list of directions and some buried treasure. And the buried treasure, it's panning away from me. The buried treasure is at some position that is equal to the number of steps that you've been given away from your starting point. So for this example, we have 2 steps, east and south. So we know that the treasure is 2 distance away. But these steps are actually lies instead of being truths. So what that means is that if the first step is E, that means the treasure is not east for the first step of your path. And the second element is S, that means for the second step you take, you're not going to be going south. So you know that they're lies. So how do we find all the possible positions of the treasure? Well, there's a fairly simple algorithm you can do to resolve this. First step is to run a BFS to find all the cells with the shortest path lengths. You know that the treasure was found on the shortest path from the starting point. That's part of the problem statement. So there's sort of no other way to find the treasure if it's not the shortest path. So we find the shortest path length to every cell relative to the starting position. The second step is we run the BFS again, but we ban all the steps that will either make the shortest path longer. We don't want to go on a path that is not the shortest because that won't lead us to the treasure. That's part of the problem statement. And we also don't want to take any steps at the current iteration that are part of this sequence. So the first step we take, we definitely don't want to go east. The second step we take, we definitely don't want to go south. And using just like an index of how many steps we've taken so far, we can see exactly what position we shouldn't be taking at any given iteration. The third step is more of an observation. It says that all cells reachable with what does that say? Insta length. Yeah, this made sense earlier. All cells that are reachable with the same initial shortest path length are also valid positions. So, if we do the initial BFS and then we do the same BFS, sort of restricting paths that increase the length and restricting paths that use these steps, and the shortest path is still the same, and the shortest path is the length of this set of instructions. So in this case, we want shortest path with a length of 2. Then we know that that could be a valid position for the treasure. And here's an example of written up. So the starting position is here, and we have some obstacles around. The first thing we do is a BFS, and we find the shortest paths to each point. This one has a shortest path of 1, this one has a shortest path of 3, etc. Then in the second BFS, we sort of rule out any paths that make things longer, and we also rule out any paths that use these steps from the instructions. And as you can see here, the resultant positions for the treasure to be, there's actually only 1. Even though there were 3 initial positions that were 2 away that could have been valid, because we can't go east on the first step or south on the second step, that narrows it down to only being 1. Cool. Let's move on. This one I sort of ran out of time to explain, but it's a very cool question. This is fruit fencer. So the objective of this question is you're essentially given a list of unit circles, and you have to find a infinite straight line that intersects as many circles as possible. A very, very important observation for this question to make is that there exists some optimal line that touches 2 of the fruits at external tangents. So, on the outside of the fruit and tangent, so perpendicular to the ray from the center to the edge. The reason for that is sort of unclear, but I intuit it like this. Basically, for every line that touches the 2 circles at tangents, represent some sort of boundary in the space of the number of circles we can intersect. There might be another solution that touches the maximum number of circles that does not have a line at 2 of the tangents, but the number of circles we intersect will change at these points where 1 line touches 2 of the tangents of the circles, and that's how we define the lines. So we actually only need to check these possible cases, both when the tangent is on the left of both of the circles and on the right of both of the circles, to find the valid solution. So that's what we do. We iterate through all ordered pairs of fruits where AB is not equal to BA. We take the tangents between the 2 circles. So when we do AB, we can go on the left. If we do BA, we can also go on the left, but because we're going from B to A instead of A to B, the tangent will end up on the other side, which is what we want. And that way we can iterate through n squared pairs of fruits, and we can basically just check if each fruit intersects with a line, which is another linear factor. So overall, this solution takes O of n cubed. Some tricks you can do to make this problem a little bit easier. You can work in integer space by multiplying all of the coordinates by 100, because of the limitations of the question. That means that all of the coordinates will be integers, which is very nice to work with. And you can also work with circle centers and discrete formulas without having to deal with the irrational coefficients that the tangents between the circles might actually have. I wanted some more time to be able to actually write these formulas down, but unfortunately I ran out. But I will be posting a PDF with sort of some more in-depth solutions from the original problem sets. So hopefully you'll be able to get some use out of those. Those are all the questions I had time to write down. Unfortunately, I also ran out of time to do problems B and C, even though they're really quite interesting and I'd recommend studying them. So keep an eye out for that editorial document that I'll be making. And the last thing I wanted to do was thank the ICPC, NCPC, and SWERC for providing the problems for this contest. I mashed a couple of contests together from my favorite problems from some of these corporations. And yeah, I hope you enjoyed them as much as I did. Do we have any questions about any of these problems I went through, or the other problems I can talk about?